Hey everyone, in this video we're going to talk about rolling contact bearings and specifically looking at a combined thrust and axial loading example. This video is part of a lecture series on mechanical design too. So we're going to get started with a problem that needs table 11.2, so I've included table 11.2 at the top here, and we're going to look at problem 1125 specifically, but the prompt is the same for all these problems listed below. We're going to look at 1125 because 1124 is a simpler problem with no axial loading. So we're told that a 02 series single row deep groove ball bearing is to be selected from table 11.2 for the application conditions specified in the table. And if you've watched the previous video, you'll know that in the previous video we had an example problem where we actually were given a bearing and we were supposed to find the life of that bearing. Now the problem is essentially reversed where we have the design life and we're looking for the bearing to use. Okay, and it's a little bit trickier to actually find the bearing when there is axial loading. So we'll talk about that throughout this problem. So assuming table 11.1 is applicable if needed, specify the smallest bore size from table 11.2 that can satisfy these conditions. So we're told we need to find the smallest bore size and we need to satisfy the conditions below. So what we're going to focus on is the conditions of 1125, which is 8 kilonewtons, 2 kilonewtons, 10 kilo hours, 400 revs per minute, inner rotation at 99%. And if you want to in your own time, you can really take all of these problems and try and do all of the problems. And if you want the solutions to those problems, you can reach out to me to give you the final answer, essentially. So we're going to use the appropriate parameters below to solve this specific problem. And we also have, so table 11.1 is in our formula sheet, which is on the right side here. So we have our whole formula sheet that can be used as our table 11.1. Okay, and then we have table 11.2 to search for stuff. Okay, so let's get started with this problem. So first things first, I'm going to write down the equation for C10 is equal to AFFD, and I've copied over this equation so you can write it down if you want to. And some of the stuff I want to go through is essentially what are the knowns and unknowns that we have within our system. So some of the things that we already know based on the problem are the following. So we know XD because we know LD and we know LR. So we haven't calculated LD yet, but we know that we have LD from question. Then we can also say that we have LR. LR is going to be 10 to the 6, as always. And we're told that RD is 0.99. We're also given FD, or we're not given FD, but we know that FD will be our F equivalent. And that's because we have a radial and axial load. So we can't just use FD of 8 kilonewtons. We have to include the axial load as well. Okay. The other things that we know the whole bottom of our equation here. So we have all of this. We have x0 theta, x0 as well. So we have all these terms at the bottom. And then we're also told that it's a ball bearing. So we have that A is equal to 3. And finally, we also have our application factor, which is equal. So AF is equal to 1. So we have all these terms available to us. So first things first, first thing we can calculate is our XD value, okay? And we're going to calculate our XD value first because we know we're going to have to use it in the equation. And right now we have a life that's given to us in hours. So we want to try and convert that into a life desired in revolutions so that we can then find XD. So XD is going to be equal to LD over LR, which is going to be equal to 60 times 400 for the RPM multiplied by 10 kilo hours, which is 10,000 hours. And we're going to divide all of that by 10 to the 6, and we're going to get 240. So what we're saying is our life desired is 240 times 10 to the 6. And the next term we need to find is FD. So what we're looking for in this question is we're looking for we're specifying the smallest bore size in table 11.2. And to find a appropriate bearing in table 11.2, what we need to find is C10. So that's why we're using this equation here. So our goal is to find C10, and therefore we need to find everything on the right side to be able to find C10. In the previous example problem, in the previous video, we had to rearrange this equation to find XD because we were given C10. In this case, we have to find C10. So the next step and the only step left is finding FE, or finding F desired. Okay, so we can say that we need to find FD. And in this case, FD is going to be equal to FE because we have a axial loading. So we need to convert our FR and FA to an equivalent force in the radial direction. Okay, so we're going to start with 8 kilonewtons, and FA is equal to 2 kilonewtons, and we also know that V is equal to 1 because we have inner ring rotation. And then we're going to go to table 11.1, and we're going to essentially copy over our equation. So if we go to table 11.1, we're going to find our FE through this equation, and we're going to follow the format that we followed previously to find FE. Okay, so we need to choose whether or not we're going to use x1 and y1 or x2 and y2, and we need to do so by figuring out if we have an FA over VFR that's greater than E or less than or equal to E. So let's go ahead and write that down, and then we'll start solving the problem. So we have that FE is equal to x VFR plus y FA, and we now need to find, we know what our FA over VFR is, and we're going to have to compare that to our E value. So in order to find our E value, we know that we have to find FA over C0 because our E value is based on FA over C0. Now, if we look at this and we try and find FA over C0, where do we usually find C0? C0 comes from table 11.2. The problem is that we don't have a C0 value. We don't currently have a C0 value for from table 11.2 because we haven't chosen a bearing yet. So we're kind of stuck in a position where we can't really check if FA over VFR is greater than or less than E because we don't know the bearing that we chose. So what we need to do is we need to make a guess on what bearing to choose. Now, in order to make a guess on what bearing to choose, we're not just going to do a random guess at a random bearing. That could be done, but it could take us a while to get to the right answer. So what we're actually going to do is we're going to look at our problem and kind of try and figure out, based on our problem, what does our F desired usually equal in this case? Or what is it going to be equal to or close enough? So if we have FR is equal to 8 kilonewtons and FA is equal to 2 kilonewtons, we see that the axial force is only 25% of the radial force. And typically when we have an axial force that's pretty close to the pretty far from the radial force, or at 25% or even 40%, we're going to get a higher value, but we're going to guess a FD. Okay, and what we mean by guess FD is guess FE. And the first guess of FE that we could do is say, well, let's keep it simple and let's always guess our FR value. Now, this is usually what we would do in this case, but sometimes FR is equal to 0. Okay, sometimes there's no radial force and there's only axial force. So in that case, you would have to come up with another methodology, okay? But you could guess 8 kilonewtons, you could guess 8.5, 8.3, whatever you want to do, and then you can check your solution after. So the first thing we're going to do is we're going to say, okay, let's guess FE because we have to make a guess. And based on that FE, we're going to find a C10 value that's possible. So we're going to guess that F desired is going to be approximately FR, so it's going to be 8 kilonewtons. Again, you could use 8.5, 8.2, 9, 10, it's fine too. But an easy methodology is just to use the FR to start with, especially when your FA is pretty low. Okay, so then what we can do is we can calculate C10. So we can then calculate C10 from our C10 equation, because now we have all of our values with our guess for FE. So we guessed, this was guessed at first, and so we can use the guess value to find the C10 based on our guess. So if we calculate C10 based on a guess, we find that C10 is equal to 82.5 kilonewtons. Okay, so that's our calculated C10 that we can go for. And based on that C10, we would then have to choose a bearing. So we have a C10 value that's based on our guess, and we can then go and choose a bearing based on that guess. Okay, so we're going to go to our table 11.2 and choose a bearing. So if we go to table 11.2, we're definitely going to choose a bearing that has a slightly higher C10 than our current value. And we're going to go ahead and use, so we know that we have a deep groove bearing in our question, so we can check, it says a single row deep groove ball bearing. So we're going to go here and we're going to see that the value that is higher than 82.5 is 83.2. So it would be an 85 millimeter bore. Okay. And then from that guess, we can write our C10 down and we can write our C0 down. This is going to be an initial guess for our bearing that we're going to use. And then we're going to check that that bearing actually works for the application. If it doesn't work, then we have to reiterate and redo the problem. So we'll go along and keep doing this. So we're going to write stuff down. So we said we chose a bearing. We chose the, I believe it's 85 millimeter. Let me double check. So yeah, it's an 85 millimeters. So we chose 85 millimeters. And based on 85 millimeters, we have a C10 of 83.2 kilonewtons, which is higher than 82.5. So it satisfies the fact that C10 is satisfied. And then C0 is equal to 53 kilonewtons in that case. And then we're able to then find an FA over C0. So we can write that FA over C0 is 2 over 53, which is going to be equal to 0.038. And if we go to our table, we can now find an E value equivalent to that 0.038. Okay, so we see that our 0.038 is pretty much between 0.042 and 0.028. And we're going to say that our value of E is going to be pretty much 0.23. Okay, we do a quick interpolation here just to say that it's 0.23. It could be actually 0.235 or 236, but it doesn't matter initially. It's just to see if we have x1, y1 or x2, y2 that we're going to use. Okay, so going back to our notes, we can say that E is equal to 0.23 from formula sheet. Okay, so following that, we can clearly say that FA over VFR, which is equal to 0.25, okay, we're given that it's equal to 0.25 in our question, is greater than E. And therefore, we're going to use x2 and y2 for our equation. And if we work through our table, we can find that x2 is equal to 0.56. So x2 is always equal to 0.56. And then y2 would be a value, if we go to the table really quickly, would be a value between 1.99 and 1.85. Okay, so it would be a value between the two. And by interpolating, we would get that y2 is equal to a value of 1.89. Okay, from interpolation. So then we can find a value of FE would be equal to 0.56 times 1 times 8 plus 1.89 times 2, based on the radial loading and the axial loading. And we get that the final FE value is 8.26 kilonewtons. Okay, so now we found a value of FE that we would ultimately get if we came up with a value of FA over C0 from the fact that we use an 85 millimeter bearing. The problem now is that we need to make sure that this 85 millimeter bearing can actually be used with the FE that we estimated. Okay, if the bearing cannot be used, then we need to step up our bearing and make sure that the next bearing up works. Okay, so what we're going to do is, with this FE that we found, assuming an 85 millimeter bearing would work, we then need to check that 85 millimeter works. And if it doesn't work, it means that our guess was wrong and we need to do a new guess. Okay, so check that 85 millimeter works. So what we're going to do is we're going to write C10 is equal to 1 for AF times 8.26 with everything in the brackets to the power of 1/3, okay, based on XD over all the Weibull parameters. And we get a value of 85.2 kilonewtons. Okay, now we see that we get a value of 85.2 kilonewtons, and we said that our C10 from the catalog chosen for the 85 millimeter was 83.2 kilonewtons. So we have a problem. Okay, our C10 required is greater than our C10 catalog. So that means that the bearing in the catalog is not strong enough to satisfy the radial loading as well as the axial loading based on that guess. So we're going to have to redo the problem and check that the next one up, or the 90 millimeter bearing, would work. And of course, what you could do is you could choose a bearing that's, for example, much higher than 90 millimeters and get away with the fact that it would work for any situation, but you're told in the question that you have to minimize the bearing size. Okay, so you have to make sure that you minimize the bearing size so that you're not over designing as well. So with a 90 millimeter bearing, what we need to do is we then need to repeat the steps that we're doing. So by repeating the steps, we have that C10 is equal to 95.6 kilonewtons, and C0 is now equal to 62 kilonewtons based on choosing this bearing instead. Then we can write that FA over C0 is now going to be slightly different. It's going to be 2 over 62, which is going to give you a value of 0.032. Then based on that value of 0.032, we can then, and I'm going to go a little bit faster through this, and I'll let you do this in your own time if you want to. But if you have 0.032, you'll find that you have the same criteria with E, so you still have to use X2 and Y2. And now if we interpolate, we have that Y2 is equal to 1.95, and we find that our FE, based on this bearing that we chose, our FE is actually 0.56 times 8 plus 1.95 times 2, and we get a value of 8.38 kilonewtons. Okay, so slightly higher load as an F equivalent based on this new bearing that we chose. And now we're going to do our check again. So what we're going to do is we're going to say C10 is going to be equal to, so there's two ways of doing this. One way is to recalculate everything and find our C10 with 8.38 multiplied by everything to the power of 1/3. Okay, another thing you can do is just say, well, we already calculated everything else, so what we can do is we can say that C10 could be equal to 8.38 over 8.26, which is the calculation we had done before, multiplied by 85.2. Okay, same exact thing. It's just a little bit faster to do the bottom one. The bottom one essentially just takes the value of C10 that we found with 8.26 and just takes the difference in percentage between 8.38 and then 8.26, and we get a value. So those two would give you the same value, 86.4 kilonewtons. And this would also be 86.4 kilonewtons. Okay, two different ways of calculating the value. One is slightly faster. Now, what we can say now is that our C10 calculated is equal to 86.4. And let's write down our C10 table just to make sure that it would be fine this time. So our C10 table, if we go back, is 95.6 kilonewtons. So what we can say is that so we chose a 90 millimeter bearing and we checked that the 90 millimeter bore would be acceptable. And it is because our C10 table is higher than our C10 calculated. Therefore, the bearing will be able to withstand the forces associated with our problem based on the equivalent force. So we can say at the end that therefore the 90 millimeter bore is acceptable and because our C10 table is greater than our C10 calculated. So we choose a 90 millimeter bore. Okay, so this shows you an example where you actually have to guess a value or guess a first bearing, then check for that bearing. And in this case, it didn't work the first time. It could have worked the first time. So we had to step up in bearing size, and then we checked that step up in bearing size worked, and it actually worked because our C10 that desired is less than the C10 from the table. So hopefully this makes sense, and we'll see you in the next video to explore a new concept, including rolling contact bearings. So we'll see you in the next one.